Okay, so first let's look at the definition of a function. So a function is a rule or a relation, and what does it do? It assigns to each member of one set a unique member of another set. Okay, and since we have two different sets that we're talking about, we use two different words. The members that get assigned are things in the domain, and the numbers that are, or the elements that are assigned to those things come out of the range, or sometimes you'll see the word codomain. So the easiest way to represent a function is, or to think about one, is to think about it sort of pictorially. So let's say that I have a set of stuff and another set of stuff. Okay, so function is just a rule that assigns certain things in one set to certain things in another set. Now, these don't have to be numbers. They can be anything you want. The one restriction, though, as to what makes this as a function is that we never have one thing being assigned to two different things in the range. Okay, so it's okay if, say, two different inputs give you the same output, but it's not okay if one input gives you two different outputs. So this is a function. But this is not a function. Okay, and so let's just look at a quick example of that. So if I had, for example, three things in my domain, and let's say two things in my range, then it would not be a function if this element was assigned to two different elements in my range. It's okay if two different things, or in this case, all three of them are assigned to one point. That's okay, but it's not okay for one thing to be assigned to multiple things. So as long as that doesn't happen, then you have a function. Now, we have a couple of other words that we use for things which live in the domain. So these pictures and using functions just to map as arrows between dots is a bit primitive. We want to do stuff algebraically, and so in that situation, the things over here and the things over there in the range are probably going to be numbers, and we're going to represent them algebraically with variables. Okay, so things in the domain has independent variables. Okay, so the independent variable represent things which live in the domain, and the range is the same thing, but it's the dependent variable. And we mean dependent in the sense that if I pick, say, this element in my range, it depends, or which element I get out of my range depends on which element I pick over here. So I only get this one if I pick this one over here. So this depends on my choice of points in the domain. Okay, so let's just look at a simple example of something which is a function. So let's say that we have three people, Bob, Alice, and Mike, and let's say that they are going to eat ice cream. And so let's say that there are three flavors available: chocolate, strawberry, and vanilla. And each person is going to select a flavor of ice cream. So let's say that Bob selects strawberry. That's fine. And let's say that Alice selects chocolate. And let's say that Mike also likes chocolate. So this is a function and it is a function because each person has only selected one flavor of ice cream. Okay, so what would make this not a function? So let's add in a line here. And let's say that there's a fourth person that comes along, and Steve is a smart aleck and chooses both vanilla and chocolate. Okay, so that would make this not a function, because one person in the domain, one element of my domain, has been assigned to two different elements of the range. That makes it not a function. So if the function and the domain and the range are just the stuff up here, so Bob, Alice, Mike, and then the three flavors of ice cream, that is a function. But the second that we introduce Steve in here, who likes both chocolate and vanilla, now it's no longer a function. Okay, so the next thing we're going to talk about is how functions look algebraically. Now, the easiest possible example, we would represent functions in a form like this: f of x equals something, and this something is the formula that tells us how numbers, x numbers, get assigned to y numbers. So, for example, we could have something like f of x equals x squared. So that's a very simple function. Now, one of the things that we want to look at is what's the relationship, if any, between functions, which are defined explicitly like this, and equations. This certainly is an equation, but does it also represent a function? And if I just wrote down an equation, can I say that that comes from a function? So that's what we'll look at next. Okay, so the first, or the example that we'll consider is, we'll start with an equation like this. Okay, so this is an equation. Now, this might describe a function, and it might not, but there's no obvious way to tell right this instant whether or not it does. Okay, so what we need to do is, this is a function if we can solve for one variable in terms of the others. And generally we'll solve for the variable y in terms of x, but it doesn't have to be that way. Okay, so let's take this equation and think of, can we solve this for y in terms of x? And so if we tried to do that, what would we see? The first thing we would want to do is move the x squared over to the right-hand side. And so we'd have y squared is 64 minus x squared. And then what you naturally would want to do is take the square root of both sides. and that's fine, except when you square root something squared, you actually get an absolute value, and that means that we end up with a plus or minus on the other side. So it's not enough to just say y equals the square root of 64 minus x squared. It's really could be both plus and minus. Okay, so the plus and the minus is the problem. And it's a problem because this is trying to take a number x and assign it two different values of y, namely the plus version and the minus version. Okay, so that's not going to be a function. So this isn't a function because we would be trying to assign, it assigns two y values to an x value. And that violates the definition of a function. Now, there is another way to do this graphically. So if we look at the example that I chose here, x squared plus y squared equals 64, and we think for just a few minutes about that, we remember that it describes a circle. And in fact, it also describes a circle that has radius 8. So let's draw a circle here. So graphically, we can tell whether or not something is a function, or if this equation can represent a function or describes a function by looking at what the graph of that equation is. Now in this case, it's a circle, and that's a simple geometric shape. Now you may remember from high school there's a trick for telling whether or not you have a function, and that's called using the vertical line test. So vertical line test. So what we do in the vertical line test is just take any vertical line, really all vertical lines, and I'm going to draw a whole bunch of them here. Actually, let's use a different color for this second line. So let's use pink for this line and orange for this line over here. So I'm just going to draw a whole bunch of vertical lines, in this case just 3 as sort of an example. And what the definition of a function means is, in terms of a graphical standpoint, is if I pick an x-coordinate, so if I pick a number somewhere here on my x-axis, it gets assigned to anything that's above it or below it. Now, it can only be assigned to one thing. So the stuff above it and below it can only intersect the curve at most one point. Now, we immediately see with this example that this vertical line intersects the curve twice. And so that means that this x-coordinate is assigned to two different values of y. That means it's not a function. Similarly, over here, the pink one also intersects in 2 spots. Now, you may wonder what to think about the orange one. The orange one doesn't intersect the blue circle at all, and that's okay. It just means that this value of x in the domain was not assigned to anything in the range. So the vertical line test succeeds if every single vertical line you draw intersects the curve at most once. And we'll write this out in a second. It fails if there is one vertical line that intersects the curve more than once. It's totally okay if a bunch of vertical lines never intersect the curve. It's just not okay if one single vertical line intersects more than once. Now, typically when that happens, it happens a lot. So in this case, any vertical line that I draw, with the exception of the two sort of at the ends, would intersect this circle more than once. So it fails really, really, really badly. So in just a second, we'll look at the difference between the statement of the vertical line test requiring either all vertical lines to never intersect more than once, being success, and failure being that one line intersects more than once. Okay, so back to the vertical line test and how we know whether or not failure versus success has to do with whether or not one vertical line has something happen versus every vertical line has something happen. So I'm going to illustrate this with a really silly example. Okay, so let's say that I wanted to prove, proof, all people have blue hair. Okay, now this is an absurd statement and we know it, but what would it take for me to prove that all people had blue hair? To prove it, I would have to march every single person, so person 1, and I'd have to look over at person 2, and so on. I'd have to check every single person and see whether or not they did, in fact, have blue hair. This means checking every person. Okay? And in the same way, the vertical line test succeeds if every vertical line passes, meaning that it intersects only once, or perhaps no times, but at most once. And that'll be kind of like having blue hair. Okay, so to prove the statement, we'd have to line up every single person on the planet and check one by one, do they have blue hair? To disprove is very easy. All I have to do is go out there and find that one person has decided that they're going to have green hair. Okay, so it just takes one counterexample for a statement to fail. In the context of the vertical line test, that would mean that it takes only one vertical line that intersects a curve more than once for the thing to for that to fail the vertical line test and for it to not be a function. So the moral of the story here is it just takes one counterexample to disprove something, but you have to look at every single case to prove something.